Okay, good morning, everybody. As I said to you yesterday, we're going to start with physics as our next unit. I've got my document camera set up today, so I'm going to do a note, and then I'm going to attach a link to go to a web page so you can read more on the topic. If you happen to have your textbook, I will give you some textbook pages that you can look at as well. So the idea here is we do 3 hours total a week. Part of that is listening to me talk to you about the subject. And then doing a little bit of follow-up work. And I'll try and keep it to 3 hours. So there's a lot of things we would normally learn about in this unit in optics. I am going to switch to the document camera, and I'm going to sort of do some notes. I suggest you take your own notes, whatever that looks like, so you have a record, a hard copy of the things that we're doing together. Okay, I'm just going to start and see how it goes. So I'm going to share what I've got under my document camera. Aha. Okay, see if this works for everybody. Hopefully. Okay, so our first topic we're going to do is all about the electromagnetic spectrum. So I'm going to call this note electromagnetic spectrum. Capital E, capital M for short form. Okay. And what I want you to draw is sort of a bunch of lines that look like this. So we're going to go sort of up, down within a couple lines like that. Okay. And then you're going to sort of keep the same height, but you're going to sort of make them go more like a rolling hill. Okay. And then get spacer and spacer and spacer, sort of like that. Okay. That'll have to do. So there's a pattern to these waves, and these are all the different forms of light. So we've got this tight together, back and forth kind of wave, and then we get to a more like slow moving, rolling wave. A couple of things about each of these waves is like from like here to here, which I'm going to say is like peak to peak. From that point to that point, we call that a wavelength. So it's basically the distance from the top point of one wave to the top point of the other wave. You can also go what we call trough to trough, so bottom to bottom. So from one point on the other to the same point on the next is what we call a wavelength, depending on the type of light, and we'll talk about types of light in a second. They have different wavelengths. So over here, this is quite a long wavelength compared to over here, which would be a really short wavelength. Okay, so I've used a couple words here. The top of the wave, I'll just use this one, so I'm not running on the same one. The top of it is called a crest, just like in surfing. Okay, similar to that. These aren't water waves, but similar kind of idea. And then the bottom portion is called the trough. Okay, so top is the crest, bottom is the trough. From one point to the same point on the next wave, we call the wavelength. Okay, the way I've drawn it here, I started with like ones that are tight together to ones that are really spaced out. You can see it go the opposite way. As it goes from sort of this slow or big wavelength towards, let's do this, towards this kind, the waves have more and more energy. So I'm going to write on here, increasing energy. Okay. If I am like standing here and I start getting pounded by these waves, if it's this kind of wave, it's going to have what we call a low frequency. So it's going to take a while before you get hit by the next peak. So if I'm here, it's going to be a bit of time until I feel this one get me and hit me this way. If I have this kind of wave coming at me, you can see it would be more like bang, 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 bang. I would get hit by a lot more waves in the same amount of time. So that's related to something we call frequency. So the waves have two pieces to them, their wavelength and also their frequency. And so if I have a big wavelength, I tend to have what's called a low frequency. And if I have a short wavelength, like we see here, that would have a high frequency. So you have to sort of picture this as a moving type of wave. And this is like all the different kind of waves there can be in one picture. So I could just be having this kind, okay, or I could just be having this kind, or there's a whole bunch that would be in between those two extremes. So we're just going to write on here that high frequency, okay, is going to correspond with or be linked to a short wavelength. And then a low frequency is going to be linked to a long wavelength. Okay, I hope you can still see that. All right. And then as we said, so high frequency means high energy. Okay, this type goes to this end. And low frequency, low wavelength would be low energy down on this end. So maybe I'll do like, this is kind of like in this region, and this is sort of like down in this region, is how those kind of go together like that. Okay, as examples of the two extremes. And of course, we have a whole bunch in between. I'm going to move that up a little bit. Hopefully you can see that okay. Okay, so some examples of the different kinds of types of light that are in here, or different types of rays. Up here at the top, the kind that tend to be high frequency, short wavelength are called gamma rays. Okay, and I feel like I should have capitalized that. I probably should have. Yes, this should be a capital G. It's be named after somebody. I forget. I'll have to look at that later. Okay, or maybe it has to do with the Greek alphabet. It's probably, there's a reason why that has to be capitalized. So those are gamma rays, and these are the kind that we usually associate with some sort of like nuclear radiation, super high powered, because they have lots of energy, and also because of that, kind of dangerous. So for example, I'm going to put in here that this would be the kind of radiation you might use for a medical scan. Okay, because they have to actually penetrate through you to see what's inside. Oh, that's kind of getting hard to see. All right, if I kind of shade it a bit. Also, we have radiation therapy for cancer. Because at this point, what you're trying to do is actually kill those cancerous cells. So the idea is you want to hit those cells with something that's actually quite damaging, to the point where it will kill the cells. And so you're using something that's dangerous to do good here, which sort of sounds backwards. But in this case, it makes sense when you think of the fact that you want to do some damage. And this is a way to direct the damage to cells that are dividing out of control and stop the cancer. Okay. Obviously, with the medical scan, it's not to the same extent. You don't want to do damage, but you do need to penetrate beyond the skin to see what's going on inside. It's a reason why you don't get these all the time, and they're not just like a go-to. They're done when they're needed, and they have a reason to be done, but it's not safe to get these done regularly as part of just general practice for no reason. Okay. It's also the reason that the techs and stuff like that that have these kind of roles would monitor how much they're being exposed to that radiation to keep them safe and to make sure they don't do any damage to themselves. Okay, as we go down a bit, we also have here X-rays. These aren't going to line up perfectly in any particular pattern to the picture above, but these ones are still quite high frequency. They're still high energy. And so X-rays, you're pretty familiar with those. You probably had them at the dentist office, or maybe you broke a bone, or they thought you broke a bone, and you were exposed to X-rays at that point in time. Down from there, I'm just going to go a little bit quicker because I'm realizing I don't have all the time in the world here to talk to you. Are UV rays, that's short for ultraviolet radiation. Some of you might be familiar with that as something that we get from the sun. They can be damaging. Obviously, when we're up here in the short wavelength, high frequency, you can see there's an element of risk being exposed to all of these rays. These are good in some respect because they're activating like your vitamin D and things like that, which is why you're encouraged to get out in the sun. Too much exposure, though, and they will damage the DNA. They're not as strong as these two, so they don't penetrate as deeply, but they do get into the upper layers of your skin cells. And so they can cause damage to the DNA in your skin cells, and that's why UV ray exposure is connected to skin cancer. And that would be why possibly you may choose to wear sunscreen to block that UV ray. You might also have that in your sunglasses, places you've heard of that before. It can also be used to disinfect water supplies. So I'm just going to write that one here. Some of you might have UV filtration systems on your water supply. So it's being used there to kill and disinfect because it has that ability, okay, with the amount of energy it has. All right, if we go down even further, we get into infrared rays, and you might be familiar with this from like night vision sort of stuff. It can be used to pick up heat and things like that. Motion sensors would take advantage of this. So I'm going to put a couple ones here that you might be familiar with. Night vision goggles. Okay, and they're mostly connected to sort of temperature and heat and being able to pick up on that heat and put it in an image for you. Okay, then we go down to microwaves. See, I'm running out of space. Squeeze it in because I have one more after this. Microwaves, and you're pretty familiar with those, I think, because your microwave oven you might have in your house if you have one. So these can be used for cooking food. Obviously, they can also be used for some communication and things like that. They can be used like those radar guns, stuff like that, that would be used to see your speed. So there's lots of possibilities there for that. And then the last one is radio. Okay, used for radio. And then there's FM and AM and all those pieces if you're familiar with radio. So as you can see, radio waves, even when the radio first came out, they were worried about exposure to radio waves and these waves traveling through the air and if there would be any damage. Radio's been around a really, really long time now, and there doesn't seem to be any harm related to that. They don't have enough energy to penetrate. Once you get up to here is where we start talking about the potential for harm, but then also because it can do harm, can bring that to helpful ways. And we can use them to like kill and see below the surface and all that sort of stuff. Okay, so I hope all of that makes sense. In your textbook, if you have a textbook, this is covered on pages 384 and 385. It'll sort of give some colorful pictures of what I've shown you here, right? So I'm just going to put it on the camera for now. See something like that with descriptions and pictures, okay, which you can take advantage of. There is the visible light spectrum, which we are going to spend most of our time talking about. And it is sort of just kind of right between the infrared and the ultraviolet. So right in here, okay, we have the visible light spectrum, and that's where we're going to spend some time after today. So we'll be coming back to that, talking a lot about color and things like that. So for now, I want you to hopefully be prepared to ask me any questions about this when I set up for an office hour. If you have the textbook, read along. I'm going to attach a web page for you to look at and read, which will also be some of your time this week for work. And then I have one question for you to answer, which I am going to post and then you're going to reply to as sort of your work to follow up on this. And that is, what is the most important technological device that uses a wavelength from the EM spectrum? So if this is opinion, there's no right or wrong. You have to pick something and basically justify your answers. 3 to 4 sentences would be ideal. So you're going to make your own note. Actually, I don't need to be showing you the note anymore. So I am going to turn this off. Oh, I should say before I go, you will see when you look at the textbook or you look at the article that there are numbers related to where you are on the spectrum. Okay, and it has to do with the wavelengths. So for example, we get down into radio, it could be that from crest to crest, it would be like a meter across. Where when you're down in the gamma rays, it's going to be like fractions of a nanometer across. So they get quite dramatically different. Okay, I'm going to turn this part off. Let's see how that goes. All right, back to me. I think that worked. So you are going to have that little lesson. You're going to take your note. You're going to read the follow-up article from the webpage, and then you're going to respond with your answer to their question. Because I sort of did like an office hour yesterday, I think I'm going to continue with another sort of follow-up to this or lesson tomorrow, and then do an office hour on Thursday, and I'll post the time for that. Keep in mind, you can always send me an email or ask me any questions. I think I've already spent up 20 minutes in making this. So I'd say 20 minutes of doing the note, probably another 20 minutes or so of reading the article, and then maybe 20 minutes thinking about researching, writing up your answer to the question I'm going to leave you with today. When I make your next lesson, I'm going to probably have a couple questions for you to answer, like a Google quiz kind of thing, and then teach you some new stuff related to the visible light section of the spectrum. All right. Okay. So I hope this works. I didn't see too many people respond with thumbs up to what was there yesterday. So if I don't see that from you, that means I got to follow up, make sure you're good, call home, see what's going to be a better solution. Okay. So if you can and aren't able, please let me know that this is working. All right. Thank you. And I will talk to you soon. Okay. Bye.